640 light-years from Earth, there's a planet where iron literally falls from the sky, raining down through permanent darkness on one side of a scorching world. This is not science fiction or artistic speculation. It's something astronomers have actually observed using some of the most powerful instruments ever built by human hands. The planet is called WASP-76b, and it orbits so close to its star that metals vaporize on the dayside, then cool, condense, and fall as metallic rain on the night side. You're watching the Drowsy Astronaut, and tonight we're visiting one of the most extreme worlds ever discovered beyond our solar system. This is a place where the very concept of weather takes on meanings that would be unrecognizable to anyone standing beneath Earth's familiar blue skies. You're welcome to listen closely as the details unfold, or simply let the words stay in the background as you rest, relax, or work on your own quiet projects. If you feel like sharing where you're listening from tonight, the comments are always open, and it's genuinely nice to see how many night sky wanderers gather here. And if videos like this help you relax and unwind, liking or subscribing is a simple way to support the channel and keep these calm cosmic journeys going. So, the discovery of iron rain on WASP-76b was announced in the year 2020, the result of careful observations made using an instrument called espresso. This spectrograph, attached to the Very Large Telescope in Chile, can detect the chemical signatures of elements in the atmospheres of planets orbiting distant stars. When astronomers pointed it at this particular world, they found something remarkable, hiding in the data that no one had observed before on any planet. They detected iron in the atmosphere, which was surprising enough given that iron is typically a solid metal under most conditions we experience on Earth. But what truly captured their attention was where the iron appeared and where it did not, a pattern that told a story about what happens on this world. The iron signature was strong on the evening side of the planet, where the dayside transitions into the night side along the terminator line that divides light from darkness. On the morning side, where the night side transitions back into day, the iron signature was absent or significantly weakened, as if the iron had somehow disappeared during the night. The explanation that emerged from this observation was both elegant and extraordinary, painting a picture of atmospheric chemistry unlike anything in our solar system. Iron vaporizes on the superheated day side, gets carried by powerful winds toward the cooler night side, and then condenses and falls as liquid metal rain before it can complete the circuit. This means that somewhere on WASP-76b, right now as you listen to these words, iron droplets may be falling through an alien sky of perpetual darkness. The rain never stops because the conditions that create it never change. The day side always blazing, the night side always comparatively cooler, the winds always blowing. It is a world of eternal weather, a cycle that has likely continued for millions or billions of years without interruption. The planet itself is a gas giant, similar in basic composition to Jupiter, but subjected to conditions that would be utterly foreign to anything in our solar system. It contains no solid surface where one could stand and watch the iron rain fall, only layers upon layers of atmosphere growing denser and hotter with depth. If you could somehow descend through those alien clouds, you would eventually reach regions where the pressure and temperature become so extreme that the distinction between gas and liquid loses meaning entirely. WASP-76b orbits its parent star at a distance that seems almost impossibly close, completing one full orbit in just 1.8 Earth days. This means that a year on this world, one complete journey around its star, takes less than 2 of our ordinary days to complete here on Earth. The proximity to its star is what creates the extreme temperatures that make iron rain possible, a cosmic circumstance that has transformed this world into something extraordinary. The planet is roughly twice the diameter of Jupiter, making it significantly larger than the biggest planet in our own solar system by a considerable margin. Despite its greater size, it may have a similar mass to Jupiter, which would make it much less dense, a puffed-up giant bloated by the intense heat of its nearby star. This inflation is common among hot Jupiters, planets that orbit so close to their stars that their atmospheres expand outward like bread rising in an oven. From Earth, we cannot see this planet directly. It is far too distant and too close to the glare of its parent star for direct imaging with current technology. Everything we know about WASP-76b comes from indirect observation, from studying how the planet affects the light of its star as it passes in front and behind it. Yet from these subtle measurements, astronomers have reconstructed a remarkably detailed picture of conditions on this distant world. The name WASP-76b follows the conventions used for planets discovered by the Wide-Angle Search for Planets survey, which has identified many worlds orbiting distant stars. The B suffix indicates that this is a planet orbiting the star, as opposed to the star itself, following the standard naming conventions of exoplanet astronomy. It is not a particularly poetic name, but it connects this world to the systematic search that revealed its existence among the countless stars of our galaxy. The discovery of this planet came years before the detection of iron rain, with the initial identification occurring back in the year 2016, when astronomers first noticed the telltale dimming. Every 1.8 days, the star WASP-76 dimmed slightly as the planet passed in front of it, blocking a small fraction of the starlight from reaching Earth. This transit method has revealed thousands of exoplanets, each one a world with its own unique characteristics, waiting to be explored and understood by patient observers. What makes WASP-76b special among the many thousands of known exoplanets is the extreme nature of its atmosphere and the clarity with which we can study it. Because the planet is so large and so close to its star, it presents an excellent target for atmospheric characterization using spectroscopic techniques available to us today. The same size that makes it inhospitable by our standards makes it an ideal laboratory for understanding atmospheric chemistry under extreme conditions. The iron rain discovery demonstrated what becomes possible when we turn our most sophisticated instruments toward carefully chosen targets in the night sky. This planet had been known for years, but the technology needed to detect iron in its atmosphere required the precision of espresso and the careful analysis of a dedicated research team. Science builds upon itself, each generation of instruments revealing secrets that previous generations could only dream of uncovering. As you settle in tonight, consider that the light from WASP-76b's parent star takes roughly 640 years to reach us across the darkness of space. The photons that astronomers capture in their telescopes began their journey during the late medieval period on Earth. Long before telescopes existed or anyone dreamed of detecting planets around other stars. By the time that light arrives, carrying news of iron rain and extreme temperatures, centuries have passed on our small blue world. This planet exists in the constellation Pisces, a region of sky that ancient astronomers associated with fish swimming through the celestial waters that they imagined above them. They could never have known that within this familiar pattern of stars lay worlds so strange they would have seemed like pure fantasy or impossible dreams. The universe has a way of exceeding our imagination, presenting us with realities more extraordinary than any myth or legend ever conceived by human storytellers. WASP-76b is one of a growing category of planets known as ultra-hot Jupiters, gas giants that orbit so close to their stars that their daysides reach temperatures above 2,000 degrees Celsius. These worlds exist in a realm of chemistry that has no parallel anywhere in our solar system, where metals become gases and familiar materials behave in unfamiliar ways. They challenge our assumptions about what planets can be and what conditions can exist on worlds beyond our own familiar home. To truly appreciate WASP-76b, we must try to imagine what conditions are like on this world, even though they exceed anything in human experience. The planet has no solid surface, no ground to stand on, no landscape in any conventional sense that we would recognize from our experience on Earth. Instead, there are only layers of atmosphere, growing denser and hotter as you descend, until eventually you reach regions where the concept of atmosphere itself becomes meaningless. If you could somehow approach this world from space, the first thing you might notice is the dramatic difference between its two hemispheres separated by the terminator line. The dayside glows with intense heat, radiating energy back into space at temperatures that would vaporize most materials we consider solid on Earth. The night side, though cooler still, maintains temperatures around 1,500 degrees Celsius, hot enough to melt iron into liquid form, allowing it to fall as rain. The planet does not rotate in the way Earth does, with familiar cycles of day and night alternating across its surface over the course of hours. Instead, it is tidally locked, meaning one face perpetually points towards its star while the opposite face remains forever turned away from that blazing source of light and heat. This creates a world of eternal moon on one hemisphere and eternal midnight on the other, with the terminator line marking the permanent boundary between these two distinct realms. On the dayside, temperatures soar to approximately 2,400 degrees Celsius, far exceeding the melting point of most metals and many rocks that form solid ground here on Earth. At these temperatures, iron exists not as the solid metal we know from everyday experience, but as individual atoms floating freely in the atmosphere as vapor. The same is likely true of many other metals, perhaps titanium, magnesium, sodium, and others we normally think of as fundamentally solid substances under any reasonable conditions. The atmosphere on this side of the planet would glow with heat, radiating in wavelengths that our eyes might perceive as a deep, angry red or orange if we could somehow witness it directly. There are no clouds in the traditional sense, no water vapor condensing into familiar white formations, but there may be hazes of vaporized minerals suspended in the superheated air above. The sky itself might seem to burn, filled with the incandescent glow of a world pushed to the extreme edges of what planetary science considers possible. Looking up from within this dayside atmosphere, if such a thing were imaginable, you would see the star WASP-76 dominating the sky overhead, enormous and intense and never moving from its fixed position. The star would appear much larger than our Sun appears from Earth, not because it is dramatically bigger, but because the planet orbits so incredibly close to its stellar parent. That unblinking eye of light would pour radiation down continuously, maintaining the temperatures that vaporize iron and drive the extreme chemistry of this world. There would be no weather in the sense we understand on Earth. No passing storms or clearing skies or seasonal changes to mark the passage of time on this side. The conditions remain essentially constant. An eternal state of superheated atmosphere beneath an eternal noon that has persisted for as long as the planet has occupied this orbit. Time would feel meaningless here, if anything could exist to perceive it, just the endless present of extreme heat radiating outward into space. Cross the terminator line into the night side, and conditions change dramatically, though they remain utterly hostile to life as we understand it on our world. The temperature drops by nearly 1,000 degrees Celsius as you move away from the stellar glare, entering a realm of permanent darkness that has never known direct light. 1,500 degrees is still extraordinarily hot by human standards, but it is cool enough for iron vapor to condense into liquid droplets that then begin to fall. This is where the iron rain occurs, in the darkness of the eternal night, falling from an atmosphere that received its iron cargo from winds blowing across from the superheated dayside. The droplets of liquid iron would glow with their own heat as they fell, tiny points of orange-red light descending through the darkness like an endless meteor shower in reverse. This rain never reaches a surface because there is no surface to reach, just deeper and denser layers of atmosphere, where the iron eventually re-vaporizes or becomes part of the complex lower atmosphere. The night-side sky would be utterly black, no star visible directly overhead, since the planet's own bulk blocks the light from the parent star completely on this hemisphere. Any illumination would come from the glow of the falling iron droplets themselves, and perhaps from the faint light scattered around the edges of the planet from the nearby terminator zone. It is a realm of darkness lit only by the precipitation of molten metal, a kind of hellish twilight that exists nowhere else we have ever observed. Winds on this world are powerful beyond anything experienced on Earth, driven by the enormous temperature difference between the day and night hemispheres of the planet. These winds may reach speeds of several kilometers per second, carrying atmospheric contents from the blazing dayside toward the cooler night side in a perpetual circulation pattern. The iron vapor that forms on the day side gets swept up in these winds and transported across the terminator, where cooling causes it to condense and fall. The terminator line itself, that boundary between permanent day and permanent night, may be one of the most dynamic regions on the entire planet. Here, temperatures transition rapidly over a relatively short distance, creating gradients that drive complex atmospheric chemistry and fierce weather patterns unlike anything on Earth. The evening terminator, where day transitions into night, is where astronomers detected the strongest signatures of iron in the atmosphere during observations with the espresso instrument. This makes sense when you consider the journey that iron atoms take across the face of this world, carried by global wind patterns from their origin in the dayside inferno. As the iron-laden atmosphere crosses into the night side, it begins to cool, and the iron starts to condense into the liquid droplets that will eventually fall as rain in the darkness ahead. The evening terminator captures this transition moment, when iron is still present in the upper atmosphere, but beginning to rain out below. On the morning terminator, where night transitions back into day, the iron signature is much weaker or absent entirely. as the astronomers observed in their groundbreaking study. This suggests that the iron has already rained out during the nightside crossing, falling into deeper atmospheric layers where it is no longer detectable by our instruments. As this iron-depleted atmosphere crosses back into the dayside, it begins to heat up again, ready to receive fresh iron vapor from the superheated regions below. This creates a global iron cycle, a perpetual circulation of metal, from vapor to liquid to vapor again, driven by the temperature differences between the two hemispheres. It is weather on a scale and of a type that has no equivalent anywhere in our solar system, a phenomenon unique to these extreme ultra-hot Jupiters. The cycle has likely continued for billions of years, iron endlessly vaporizing and raining and vaporizing again in a loop that never varies. If you could somehow hover in the upper atmosphere of WASP-76b and survive the lethal conditions, you would witness a world of stark and terrifying beauty. The dayside would blaze with light and heat, the atmosphere itself glowing like the interior of a furnace, metal atoms shimmering in the superheated air around you. Winds would tear past at tremendous speeds, carrying you toward the nightside whether you wished to go or not, part of the great atmospheric circulation. Crossing into the night, you would enter darkness, illuminated only by falling drops of liquid iron, each one glowing orange-red as it descended through the blackness toward depths unknown below. The temperature would drop, though it would still be hot enough to destroy any material or machine we could currently build, and the iron rain would continue endlessly around you. There would be no dawn coming, no sunrise to mark the end of night, just the eternal darkness of a hemisphere that never sees its star. This is WASP-76b, a world of fire and metal, of eternal day and eternal night, of iron rain falling through darkness on one side, while iron vaporizes into the sky on the other. It is real, it exists right now as you listen to these words, and it will continue to exist long after everyone alive today has passed into memory and history. The universe creates such wonders casually as natural consequences of physics and orbital mechanics. Extraordinary to us, but ordinary to the cosmos. In the next part of our journey, we will explore what kind of planet this truly is, and how it came to occupy such an extreme orbit around its star. The story of ultra-hot Jupiters is a story of planetary migration, of worlds that formed in one place and moved to another, finding themselves in environments their original formation could never have anticipated. WASP-76b belongs to a category of exoplanets that astronomers call ultra-hot Jupiters, gas giants that orbit so close to their stars that their atmospheres reach extraordinary temperatures. These worlds are among the most extreme planets we have discovered, pushed to conditions that challenge our understanding of what planetary atmospheres can become under intense stellar radiation. They are laboratories for exotic chemistry, places where familiar materials behave in unfamiliar ways that we are only beginning to comprehend. The term hot Jupiter was coined in the early days of exoplanet discovery, when astronomers first realized that gas giants could exist in orbits much closer to their stars than anything in our solar system. The first exoplanet found around a sun-like star, discovered in 1995, was itself a hot Jupiter, orbiting its star in just 4 days and overturning assumptions about where giant planets could exist. Since then, hundreds of hot Jupiters have been discovered, each one expanding our understanding of planetary diversity. Ultra-hot Jupiters represent the most extreme end of this category. worlds where dayside temperatures exceed approximately 2,000 degrees Celsius, and atmospheric chemistry enters truly exotic regimes. WASP-76b, with its temperatures reaching 2,400 degrees, sits comfortably within this ultra-hot category among the most extreme worlds we have discovered. These planets blur the line between what we consider a planet and what we might consider a very cool star, at least in terms of their atmospheric temperatures. The size of WASP-76b is impressive, approximately 1.8 times the diameter of Jupiter, making it significantly larger than the biggest planet in our own solar system. This places it among the larger gas giants we have discovered, though not exceptionally so. Some exoplanets are even bigger, approaching the size threshold where they would begin nuclear fusion and become stars. The planet's mass is roughly 85% that of Jupiter, meaning it is less dense than our solar system's giant, puffed up by the intense heat from its nearby star. This inflation is a common feature of hot Jupiters, a consequence of the intense stellar radiation that heats their upper atmospheres and causes them to expand outward into space. The same amount of material that would form a Jupiter-sized planet in the cold outer reaches of a solar system will form a much larger planet when subjected to the intense heat of a close-in orbit. WASP-76b would likely be considerably smaller if it orbited at the same distance as Jupiter does from our Sun. The planet's density, or rather, its lack of density, tells us something about its internal structure and composition beneath those visible outer atmospheric layers. Like Jupiter, it is composed primarily of hydrogen and helium, the most abundant elements in the universe, with smaller amounts of heavier elements mixed throughout its bulk. The heat from the nearby star has expanded this material outward, creating a planet that is almost like a balloon, large in volume but relatively low in mass for its apparent size. One of the most intriguing questions about ultra-hot Jupiters is how they came to occupy orbits so close to their stars, positions that seem almost impossibly dangerous. The standard model of planetary formation suggests that gas giants should form beyond the frost line in a solar system, the distance where volatile compounds like water can condense into solid ice and contribute to planetary cores. This region is typically several astronomical units from the star, far beyond the scorching inner regions where ultra-hot Jupiters are found today. The most widely accepted explanation is planetary migration, a process by which planets move from their original formation location to different orbits over time during the early chaotic years of a solar system. Interactions with the disk of gas and dust that surrounds young stars can cause planets to spiral inward, losing orbital energy and moving closer to their stellar parents. This process can transport a gas giant from the cold outer regions to the scorching inner zones where we find hot and ultra-hot Jupiters today. The migration process is not gentle or orderly, and the gravitational interactions that drive it can also fling other planets out of their systems entirely, creating the chaos we see in many exoplanetary systems. Some hot Jupiters may have migrated inward by gravitationally scattering off other massive planets, exchanging orbital energy in close encounters that sent them plunging toward their stars. Others may have been influenced by distant stellar companions, binary partners that perturbed their orbits over millions of years of gravitational interaction. The orbit of WASP-76b, with its period of just 1.8 Earth days, places the planet incredibly close to its parent star by any reasonable standard. The distance from star to planet is only about 3% of the distance between Earth and our Sun, a proximity that exposes the planet to intense radiation and gravitational forces. At such close range, the star would appear enormous in the planet's sky, dominating the heavens on the side that faces it perpetually. This proximity also means that the planet's year, one complete orbit around its star, is shorter than 2 Earth days, a concept that challenges our intuitive sense of what years and days should mean. While Earth takes 365 days to orbit the Sun, WASP-76b completes over 200 orbits in the same period of time, racing around its star at tremendous speed. The velocity required to maintain such a close orbit is much higher than Earth's orbital velocity, perhaps 100 kilometers per second or more. The gravitational forces at such close range are also responsible for the planet's tidal locking, the phenomenon that keeps one face always pointing toward the star. When a planet orbits close to its star, gravitational tides raise bulges in its atmosphere and interior, similar to how our moon raises tides in Earth's oceans. Over time, these tides dissipate energy from the planet's rotation, gradually slowing its spin until one face remains permanently locked toward the source of gravitational attraction. Ultra-hot Jupiters like WASP-76b represent a population of planets that likely exists in only a small fraction of planetary systems throughout the galaxy at any given moment. Many hot Jupiters are slowly spiraling inward towards their stars, their orbits decaying over millions or billions of years due to tidal interactions with their stellar hosts. Eventually, some of these planets will spiral close enough to be torn apart by gravitational forces or swallowed entirely by their expanding stars. This means that the ultra-hot Jupiters we observe today may represent a transitional phase in planetary evolution, a brief period before their eventual destruction in astronomical terms. The word brief here means millions or billions of years, timescales that are unimaginably long by human standards, but short by the standards of stellar and planetary lifetimes. We are witnessing these worlds in a particular moment of their existence, capturing snapshots of planets on journeys toward eventual fates we can predict but not witness. WASP-76b itself may eventually meet such a fate, spiraling ever closer to its star until tidal forces tear it apart or the star expands enough to engulf it entirely. But that day, if it comes, lies far in the future, long after human civilization has either spread to the stars or faded into history, along with countless species before us. For now, the planet continues its rapid orbit, iron reigning on its nightside, conditions extreme but stable on timescales that matter to current observers. In the next part of our journey, we will explore what it means for this world to be tidally locked, forever divided between eternal day and eternal night. This division creates 2 worlds on a single planet, each with its own character and conditions, connected only by the fierce winds that circulate between them. The tidal locking of WASP-76b creates one of its most defining features, the permanent division between a hemisphere of eternal day and a hemisphere of eternal night. This phenomenon occurs when a planet's rotation period matches its orbital period exactly, so that one face always points toward the star, while the opposite face always points away into the darkness. Many planets orbiting close to their stars experience this effect, their rotations gradually slowed by gravitational forces until they become locked in this configuration. On Earth, we experience the gentle rhythm of day and night as our planet rotates on its axis, each location cycling through periods of light and darkness roughly every 24 hours. This rhythm has shaped the evolution of life, creating creatures that are active during the day, others that emerge at night, and still others that thrive in the twilight transitions between these two states. The very concept of time for most of human history was tied to this cycle of light and darkness that seemed as natural and inevitable as existence itself. WASP-76b knows no such rhythm, no alternation between light and darkness to mark the passage of time or create the conditions for different modes of existence. The dayside has been blazing continuously for as long as the planet has occupied its current tidally locked configuration, perhaps for billions of years without interruption. The nightside has been dark for equally long, never knowing the touch of direct starlight from its nearby stellar parent. The terminator line that separates these two hemispheres runs around the planet like a great circle, a permanent boundary between two entirely different realms of existence. This is not a gradual transition, but a relatively sharp one, with conditions changing dramatically over distances that are small compared to the planet's overall size and diameter. The terminator is a zone of twilight, where the star sits forever on the horizon, never rising and never setting, fixed in a permanent position. On the dayside, just beyond the terminator, temperatures already reach levels that would be considered extreme by any Earth-based standard, metals beginning to approach their vaporization points. Moving further into the dayside, conditions become progressively more intense until you reach the substellar point, the location where the star appears directly overhead at all times. This is the hottest region on the planet, ground zero for the stellar radiation that drives all of the extreme chemistry we have discussed throughout this journey. The substellar point on WASP-76b experiences the full intensity of its nearby star, unfiltered by any planetary rotation that might distribute this heat around the globe over time. The temperature here reaches approximately 2400 degrees Celsius, hot enough to vaporize iron and many other metals we consider solid under normal circumstances. This heat radiates outward from the substellar point, creating temperature gradients that decrease as you move toward the terminator and the cooler nightside beyond. The nightside, in contrast, exists in perpetual shadow, never receiving direct radiation from the star that dominates its dayside companion hemisphere so completely. This does not mean the nightside is cold by human standards. At approximately 1500 degrees Celsius, it would still be utterly lethal to any technology we could currently build. The nightside receives its heat from atmospheric circulation, winds that carry thermal energy from the dayside across the terminator in a never-ending exchange. Without these winds, the nightside would cool much more dramatically, potentially reaching temperatures where even gases might condense into liquids or solids in the upper atmosphere. The temperature difference between the two hemispheres would be even more extreme, creating an even sharper transition at the terminator boundary between day and night. But the atmosphere acts as a heat transport mechanism, evening out the temperature differences to some degree through the circulation of hot gas from one side to the other. The darkness on the night side is not merely an absence of light, but a permanent condition, as fundamental to that hemisphere as the blazing brightness is to the dayside. If any observer could somehow exist in that eternal night, they would never see the star that dominates the sky on the opposite side of the planet. The planet's own bulk blocks the starlight completely, creating a shadow that extends outward into space like a long, dark cone behind the illuminated dayside. The winds that blow between these two hemispheres are driven by the tremendous pressure differences created by the temperature gradient across the terminator boundary. Hot air on the dayside expands and rises, creating regions of lower pressure near the top of the atmosphere that draw in cooler air from the nightside. Cooler air on the nightside sinks and flows back toward the dayside at lower altitudes, completing a circulation pattern that operates continuously without pause. These winds may reach speeds of several kilometers per second, far exceeding any wind speeds ever recorded on Earth or anywhere else in our solar system. The most powerful hurricanes on Earth have sustained winds of perhaps 300 kilometers per hour, while the winds on WASP-76b may exceed 10,000 kilometers per hour in their most intense regions. These are not storms in any conventional sense, but rather permanent features of the atmospheric circulation pattern. The iron vapor that forms on the dayside becomes entrained in these winds, carried along as part of the atmospheric circulation toward the cooler nightside hemisphere. As the iron-laden air crosses the terminator, it begins to cool, and the iron vapor starts to condense into liquid droplets that grow larger as they absorb more condensing iron atoms. Eventually, these droplets become heavy enough to fall, beginning their descent as the iron rain that made this planet famous. The transition zones near the terminator may be the most dynamic regions on the entire planet, places where dayside chemistry meets nightside conditions in complex and potentially violent interactions. Temperature changes rapidly over relatively short distances, creating chemical gradients that drive reactions we are only beginning to understand through modeling and observation. The evening terminator, where day transitions into night, is particularly important for the iron rain cycle we have been exploring. Astronomers specifically target the terminator regions when studying planets like WASP-76b because this is where starlight passes through the atmosphere on its way to Earth. When the planet transits in front of its star, a thin ring of atmosphere around the planet's edge becomes backlit by the stellar glow. This allows astronomers to study the chemical composition of the atmosphere by analyzing which wavelengths of light are absorbed as they pass through this atmospheric ring. The detection of iron on the evening terminator, but not the morning terminator, was a crucial observation that revealed the iron rain phenomenon to astronomers studying this world. This asymmetry told a story of chemical transport, of iron vapor being carried from the dayside and condensing out before it could complete the journey back to the morning side. Without the terminator observations, we might never have understood the remarkable meteorological processes occurring on this distant world. The concept of time on a tidally locked world would be fundamentally different from our experience on Earth, where the cycling of day and night provides a natural framework for measuring the passage of hours and days. On WASP-76b, there are no sunrises or sunsets to mark boundaries between periods of activity and rest. No seasonal changes to indicate the passage of longer stretches of time. The conditions remain essentially constant at any given location. The same temperature and lighting persisting indefinitely. The only meaningful measure of time would be the orbital period itself, the 1.8 Earth days it takes for the planet to complete one circuit around its star. But even this cycle creates no observable change from the perspective of someone on the planet's surface, if such an observer could exist. Because the tidal locking ensures the star always appears in the same position relative to the ground. The orbit proceeds, but nothing visible changes as a result. This permanence, this unchanging quality of conditions on a tidally locked world, creates an almost meditative quality when contemplating what existence might mean in such a place. There is no waiting for dawn because dawn never comes. No anticipation of evening because evening has no meaning on the eternal dayside. or the eternal nightside. Time passes, but nothing marks its passage, except perhaps the slow processes of atmospheric chemistry continuing their endless cycles without beginning or end. In the next part of our journey, we will descend deeper into the dayside inferno, exploring the extreme conditions that exist in the hottest regions of this remarkable world. The dayside of WASP-76b represents one of the most extreme environments we have ever discovered on any planet orbiting a distant star. Temperatures in this region reach approximately 2,400 degrees Celsius, exceeding the melting points of most metals and many materials we consider the building blocks of solid worlds. This is not a place of rock and metal in any form we would recognize, but rather a realm of vaporized minerals floating in an atmosphere of superheated gases. At the substellar point, where the parent star hangs directly overhead in an eternal noon, the intensity of stellar radiation reaches its maximum possible value for this planet. The star WASP-76 is larger and hotter than our Sun, pouring energy onto this hemisphere at a rate that would be difficult to comprehend in human terms. Every second, enormous quantities of radiation strike the dayside atmosphere, heating it to temperatures that blur the line between what we consider gas and what we consider plasma. The atmosphere in this region glows with its own heat, radiating energy back into space at wavelengths that extend from the visible red through the infrared portion of the electromagnetic spectrum. If you could somehow view this hemisphere from space with eyes sensitive to infrared light, it would appear to blaze like a dim star, radiant with the heat it absorbs and re-emits. This thermal glow is one of the ways astronomers study these planets, measuring the heat they radiate to determine their temperatures. The chemistry of the dayside atmosphere is unlike anything found on Earth or anywhere else in our solar system. An exotic mixture of vaporized metals and minerals suspended in hydrogen and helium. Iron exists here not as the solid metal we use to build bridges and buildings, but as individual atoms floating freely in the superheated gas around them. The same is true of other metals that we normally encounter only in solid form. Titanium, magnesium, calcium, and many others may all exist as vapors in this extreme environment. Some molecules can survive even at these temperatures, though they are very different from the molecules we find in cooler planetary atmospheres, like Earth's own protective layer. Titanium oxide and vanadium oxide may be present, molecules that form when metal atoms combine with oxygen under high temperature conditions that would destroy most other chemical bonds. These molecules absorb light in distinctive ways, creating signatures that astronomers can detect from across the vast distances of interstellar space. The absence of water vapor on the dayside is notable, a stark contrast to planets like Earth, where water is a major component of the atmosphere and hydrosphere together. At the temperatures prevailing on the dayside of WASP-76b, water molecules would be completely dissociated, broken apart into their component hydrogen and oxygen atoms by the sheer thermal energy of the environment. There are no clouds of water vapor here, no possibility of familiar rain, only the exotic precipitation of metals that condenses on the cooler night side. Looking upward from within this dayside atmosphere, purely as an exercise of imagination, since no observer could survive here, you would see the star WASP-76 dominating the sky in perpetuity. The star would appear larger than our Sun does from Earth, subtending a greater angle in the sky due to the extreme proximity of the planet's orbit. This enormous stellar disk would never move, never set, never change position, fixed eternally at whatever angle corresponds to your location on the dayside hemisphere. The color of the light would be slightly different from sunlight, shifted toward the blue end of the spectrum, because the star is hotter and more luminous than our sun. This blue-white light would illuminate the roiling atmosphere below, though illuminate may not be quite the right word for conditions where the atmosphere itself glows with thermal radiation. The distinction between the light coming from the star and the light emitted by the heated atmosphere might be difficult to perceive under such extreme circumstances. There would be no landscape to observe in any conventional sense, no mountains or valleys or surfaces of any kind to break the monotony of the glowing atmospheric layers stretching to every horizon. The concept of a horizon itself becomes unclear when there is no surface from which to observe, only the gradual thickening of atmospheric layers as you descend deeper into the planet's gravitational embrace. This is a world without ground, without solidity, without anything a human would recognize as a place to stand. The pressure within the dayside atmosphere increases dramatically as you descend from the upper layers where starlight first makes contact with the planet's gaseous envelope. At the levels where iron vapor exists, the pressure may still be relatively low, comparable perhaps to the upper atmosphere of Earth or even the near vacuum of space. But descend far enough and the pressure rises to values that would crush any material or structure we could build today. Deep within the planet, the pressure becomes so intense that the gases begin to behave like liquids, compressed so tightly that the distinction between these states of matter loses its familiar meaning. Even deeper, under pressures millions of times greater than Earth's surface atmosphere, hydrogen itself may transition into a metallic state, conducting electricity like a metal, while remaining in some sense a fluid. These conditions exist deep within Jupiter as well, but the temperatures on WASP-76b add another layer of extremity. The heat from the star does not penetrate to these deepest layers. The atmosphere above absorbs the stellar radiation long before it could reach such depths. Instead, the deep interior of the planet retains heat from its formation, slowly radiating this primordial energy outward over billions of years. This internal heat contributes to the overall temperature profile of the planet, adding to the stellar heating of the outer layers to create conditions extreme beyond our everyday comprehension. The boundary between the atmosphere and the deeper interior is not sharp but gradual, a continuous transition from gas to supercritical fluid to metallic hydrogen as pressure and temperature increase together. There is no surface where the atmosphere ends and something else begins. No dividing line that you could point to and say, here is where the planet becomes solid. This is fundamentally different from rocky planets like Earth, where a clear distinction exists between the gaseous atmosphere and the solid ground beneath. This lack of a surface means that the concept of weather on WASP-76b is purely atmospheric, involving the movement and transformation of gases rather than their interaction with solid landforms or liquid oceans. There are no mountains to block winds, no oceans to absorb heat, no continents to create differential heating between land and sea. Everything happens in the three-dimensional realm of the atmosphere itself. Layers upon layers of gas extending from the visible cloud tops down to the unimaginable depths below. The dayside inferno continues its eternal blaze, iron vaporizing into the superheated air, winds carrying this metallic vapor toward the terminator, where cooler temperatures await beyond the boundary. This process has continued for as long as the planet has occupied its current orbit, and will continue for as long as the star continues to shine and the planet continues to receive its intense radiation. There is no beginning and no end to this cycle, only the eternal present of extreme conditions persisting unchanged. In the next part of our journey, we will explore the physics of how iron becomes vapor, examining what happens at the molecular level when temperatures rise high enough to transform solid metal into gas. The transformation of iron from solid metal to invisible vapor represents one of the most striking aspects of the extreme conditions found on WASP-76b. On Earth, we encounter iron as one of the most important solid materials in our civilization, the backbone of our buildings, vehicles, and countless tools we use every day. The idea that iron could exist as a gas, floating freely in an atmosphere like water vapor in our air, seems almost impossible at first consideration. Yet physics cares nothing for our intuitions, and at high enough temperatures, all materials will eventually transition from solid to liquid to gas, following the fundamental rules that govern matter throughout the universe. Iron melts at approximately 1538 degrees Celsius, becoming the liquid metal that has been used in forges and foundries for millennia of human metalworking history. At even higher temperatures, around 20 to 860 degrees Celsius, iron begins to boil, transitioning from liquid to gas, just as water does at 100 degrees. On the dayside of WASP-76b, temperatures exceed these boiling points by comfortable margins, ensuring that iron exists entirely in its gaseous phase in the upper atmospheric layers. The iron atoms float individually in the surrounding atmosphere, no longer bound to other iron atoms in the crystalline structure that gives solid iron its familiar properties. These atoms drift with the winds, carried along as part of the atmospheric circulation that ultimately transports them toward the cooler nightside. The process of vaporization requires energy, the input of thermal energy that breaks the bonds holding atoms together in their solid or liquid configurations. Each iron atom that transitions from liquid to gas must absorb a certain amount of energy, called the latent heat of vaporization, to overcome the attractive forces binding it to its neighbors. On WASP-76b, this energy is abundantly available, supplied continuously by the intense radiation from the nearby parent star. At the molecular level, the iron atoms in the dayside atmosphere are in constant motion, vibrating and colliding with other atoms and molecules in the surrounding gas at tremendous speeds. The temperature of a gas is directly related to the average kinetic energy of its constituent particles. So the high temperatures on the dayside correspond to iron atoms moving very quickly indeed. These rapid motions help keep the atoms suspended in the atmosphere, preventing them from settling downward under the influence of gravity alone. The iron does not exist in isolation, but rather as part of a complex atmospheric mixture containing hydrogen, helium, and numerous other elements and compounds in varying states. The iron atoms collide with hydrogen molecules, helium atoms, and other metallic vapors, exchanging energy in each collision and maintaining the thermal equilibrium of the atmospheric layer. This is a dynamic environment, atoms and molecules constantly interacting while being carried along by the powerful winds that circulate around the planet. Other metals besides iron almost certainly exist as vapors in the dayside atmosphere, though iron has received the most attention due to its clear detection in observational data. Titanium has a boiling point of around 30 to 100 degrees Celsius, still within reach of the hottest regions of the dayside, where temperatures approach 2400 degrees or higher in some models. The detection of titanium oxide in some ultra-hot Jupiter atmospheres suggests that titanium is indeed present in gaseous form, combined with oxygen atoms. Magnesium, with a boiling point of around 1100 degrees Celsius, would vaporize even more readily than iron under the conditions prevailing on the dayside of this extreme world. Sodium and potassium, alkali metals with relatively low boiling points, have been detected in the atmospheres of various hot Jupiters and likely exist on WASP-76b as well. The atmosphere is probably a rich mixture of metallic vapors, each element contributing its own spectral signatures to the light that passes through on its way to Earth. Even some rocky materials might exist as vapors in the hottest regions of the dayside atmosphere, silicates and other minerals that form the solid crust of Earth and other rocky planets. At temperatures approaching 2500 degrees Celsius, certain rock-forming compounds can vaporize, adding their constituents to the exotic atmospheric mixture. This raises the possibility of truly strange precipitation on the night side, not just iron rain, but perhaps rain of other metals, or even vaporized rock condensing into droplets. The spectroscopic detection of iron in the atmosphere of WASP-76b relied on the distinctive way iron atoms absorb light at specific wavelengths determined by their electronic structure. Every element has a unique pattern of absorption lines, wavelengths at which it preferentially absorbs passing light, creating a fingerprint that allows astronomers to identify its presence from great distances. Iron has numerous such lines throughout the visible and near-infrared spectrum, making it relatively easy to detect when present in sufficient quantities. When the planet transits in front of its star, a small amount of starlight passes through the thin ring of atmosphere at the planet's edge, before continuing on toward Earth and our waiting telescopes. This light carries the imprint of whatever atoms and molecules it encountered during its passage through the atmosphere, with certain wavelengths slightly dimmed by absorption. By comparing the transit spectrum to the star's normal spectrum, astronomers can identify which elements are present in the planetary atmosphere and in what approximate quantities. The espresso spectrograph that detected iron on WASP-76b is one of the most precise instruments of its kind ever built, capable of detecting very subtle changes in the spectrum of starlight. Its name stands for a shell spectrograph for rocky exoplanets and stable spectroscopic observations, reflecting its original design goal of detecting small rocky planets through the radial velocity method. But its extreme precision also makes it ideal for studying the atmospheres of larger planets like WASP-76b. The transition from iron vapor to iron rain occurs when the temperature drops enough for the vapor to condense, a process that requires the removal of the same latent heat that was added during vaporization. As iron-laden atmosphere crosses from the dayside to the nightside, the temperature gradually decreases and eventually falls below the point where iron vapor can remain stable in gaseous form. At this point, iron atoms begin to stick together, forming tiny droplets of liquid iron that grow larger as more atoms condense onto their surfaces. These droplets are initially microscopic, perhaps only a few atoms across, but they grow as the condensation process continues in the cooling atmospheric stream. Larger droplets are heavier and more prone to falling under the influence of gravity, while smaller droplets may remain suspended in the atmospheric flow for longer periods. Eventually, the droplets reach sizes where gravitational settling overcomes atmospheric buoyancy, and they begin their descent as the iron rain that has made this planet famous. The falling iron droplets glow with their own heat, still at temperatures of around 1500 degrees Celsius, even on the cooler night side where the rain occurs. This is far above iron's melting point of 1530 to 8 degrees, meaning the droplets remain liquid throughout their fall rather than freezing into solid particles. The night side of WASP-76b is lit by this falling rain, droplets of liquid metal glowing orange as they descend through the eternal darkness. Next, we will explore the powerful winds that carry iron vapor from the dayside to the night side, examining the atmospheric circulation patterns that drive this remarkable weather system. The atmospheric circulation on WASP-76b is driven by one of the most extreme temperature gradients found on any known planet, the difference between the blazing dayside and the cooler night side. This temperature difference creates pressure differences in the atmosphere, with hot air expanding and rising on the dayside, while cooler air sinks and flows along on the night side. The result is a global circulation pattern of tremendous power, winds that race around the planet at speeds that dwarf any weather phenomenon on Earth. On Earth, our strongest hurricanes produce sustained winds of perhaps 300 kilometers per hour, powerful enough to devastate coastal cities and reshape landscapes over the course of their passage. The winds on WASP-76b may reach speeds measured in kilometers per second, thousands of times more powerful than the most extreme terrestrial weather events ever recorded. These are not storms in the sense we understand them, but rather permanent features of the atmospheric circulation, blowing continuously without beginning or end. The basic pattern of circulation involves hot air rising on the dayside, flowing at high altitude toward the night side, sinking as it cools and returning at lower altitude toward the dayside. This is similar in principle to the Hadley cells that drive tropical circulation on Earth, but operating on a much larger scale and with much greater intensity. The entire atmospheric envelope of the planet participates in this circulation, driven by the relentless input of heat from the nearby star. The iron vapor that forms on the dayside becomes entrained in these winds, carried along as part of the atmospheric mass, flowing toward the nightside terminator and beyond into permanent darkness. Individual iron atoms have no choice in this matter. They go where the wind takes them, swept along by the motion of the surrounding gas. The winds do not discriminate between iron and other atmospheric components, carrying everything together in a well-mixed flow that transports chemical species around the planet. The evening terminator, where the dayside transitions into the nightside, represents a critical region in this circulation pattern and in the iron cycle we have been exploring. Here, the iron-laden atmosphere from the dayside first begins to encounter cooler temperatures, and the condensation process begins in the upper atmospheric layers. The strong iron signature detected at the evening terminator by astronomers reflects this moment of transition. Iron still present, but beginning to rain out. By the time the atmosphere reaches the morning terminator on the other side of the night side, much of the iron has already precipitated out, falling as rain into deeper atmospheric layers. The morning terminator shows a much weaker iron signature, consistent with the idea that the iron rain has depleted the upper atmosphere of its metallic content. This asymmetry between evening and morning terminators was the key observation that revealed the iron rain phenomenon to the scientific team studying this world. The speed of the winds has important implications for the distribution of chemicals around the planet and the overall temperature structure of the atmosphere. If the winds were slow, there would be an even greater temperature difference between the two hemispheres, with less heat transported from day to night. The fact that the night side remains as warm as 1500 degrees Celsius suggests that atmospheric circulation is efficient at moving thermal energy around the planet. Computer simulations of ultra-hot Jupiter atmospheres have been developed to understand these circulation patterns in greater detail than observations alone can provide. These models solve the equations of fluid dynamics and radiative transfer, calculating how the atmosphere should behave under the extreme conditions of these worlds. They predict strong equatorial jets, winds that race around the planet at the equator, superimposed on the broader day-to-night circulation pattern. The simulations also predict that the hottest point on the planet may not be exactly at the substellar point, but rather shifted slightly eastward by the prevailing winds. This hot spot displacement has been observed on other hot Jupiters through measurements of their thermal emission as they rotate and orbit their stars. The winds carry the heated atmosphere along faster than the planet rotates beneath them, pushing the warmest regions slightly ahead of the point directly facing the star. The vertical structure of the winds is also complex, with different wind patterns potentially occurring at different altitudes within the deep atmosphere of the planet. Near the top of the atmosphere where stellar radiation is absorbed, the day-to-night flow dominates, carrying heat from the illuminated hemisphere to the dark side. Deeper in the atmosphere, other circulation patterns may develop, driven by the internal heat of the planet rather than by stellar radiation. The iron that rains out on the night side does not simply disappear from the planetary system, but rather joins the deeper atmospheric layers below the observable upper atmosphere. What happens to this iron at depth is still somewhat uncertain, depending on conditions that we cannot directly observe with current instruments. It may re-vaporize at deeper, hotter levels and eventually circulate back up to the observable atmosphere, or it may sink into even deeper layers where it becomes permanently sequestered. If the iron continuously rains out and sinks without returning to the upper atmosphere, the planet would gradually lose its iron rain over time as the upper atmospheric reservoir becomes depleted. However, the continued detection of strong iron signatures suggests that the cycle is sustainable, that iron somehow returns to the upper atmosphere to maintain the spectacular phenomenon. The deep circulation patterns of ultra-hot Jupiters remain an active area of research, with many questions still waiting for answers. The winds also affect the chemistry of the atmosphere beyond simply transporting iron and other elements from place to place around the planetary globe. Different chemical reactions occur at different temperatures and pressures, so the rapid transport of gas from hot to cool regions can freeze in chemical compositions from the hotter environment. A parcel of gas that moves quickly from the dayside to the nightside may not have time to reach chemical equilibrium at the new temperature, retaining a chemical memory of its origin. This phenomenon, sometimes called chemical disequilibrium or quenching, means that the atmospheric composition observed at the terminator may not accurately reflect the local temperature conditions there. Instead, the composition may tell us about conditions deeper in the atmosphere, or on the hotter dayside, where the gas most recently reached equilibrium. Understanding these effects requires sophisticated models that couple atmospheric dynamics with chemical reaction networks. The winds between worlds on WASP-76b represent a fascinating subject for ongoing research. A natural laboratory for understanding atmospheric physics under extreme conditions. Earth's atmosphere seems tame by comparison. Our most violent weather events merely gentle breezes next to the perpetual gale that circles this distant world. Yet the same physical principles govern both systems. The universal laws of fluid dynamics and thermodynamics applied to vastly different circumstances. Now let's return to the night side and explore the iron rain in greater detail, imagining what this remarkable precipitation might look like if anyone could somehow witness it directly. The night side of WASP-76b exists in perpetual shadow, never touched by direct light from the star that blazes so intensely on the opposite hemisphere. This eternal darkness extends across half of the planet's surface, a hemisphere-sized region of permanent night that has endured for as long as the planet has been tidally locked. It is here, in this realm of shadow, that the iron rain falls continuously through the hot, dark sky above. The rain begins in the upper atmosphere, where iron vapor carried from the dayside first encounters temperatures cool enough to trigger condensation into liquid droplets. The transition happens somewhere beyond the evening terminator, as the atmospheric stream flows further into the night side and continues to cool radiatively by shedding heat into space. Tiny droplets form first, perhaps only microscopic specks of liquid iron, nucleating around whatever particles happen to be present in the atmospheric flow. These droplets grow as more iron atoms condense onto their surfaces, the vapor pressure of iron decreasing as the temperature falls, and making it increasingly favorable for the metal to exist in liquid rather than gaseous form. Eventually, the droplets reach sizes where gravity begins to dominate over the buoyant forces that keep small particles suspended in the atmospheric flow. At this point, they begin to fall, accelerating downward into the depths of the nightside atmosphere below them. The falling iron droplets would glow with their own light, heated to approximately 1500 degrees Celsius and radiating energy in the red and near-infrared portions of the electromagnetic spectrum. If human eyes could somehow witness this scene, they would see countless points of orange-red light descending through the darkness, a continuous meteor shower that never ends. The brightness of each droplet would depend on its size and temperature, larger droplets glowing more brightly than smaller ones. This rain would not fall in sheets or curtains as rain does on Earth, but rather as a constant drizzle of individual droplets, separated by the vast empty spaces of the atmospheric volume. The density of droplets in any given volume would be relatively low compared to terrestrial rainstorms, but the continuous nature of the phenomenon would make up for the sparse distribution. At any moment, countless iron droplets are falling somewhere on the night side, part of the eternal precipitation cycle. The sound of this rain, if sound could propagate through the hydrogen-helium atmosphere in a way that human ears could perceive, there would be no patter of raindrops on surfaces, because there are no surfaces to strike, no leaves or rooftops or puddles to create the familiar sounds of terrestrial storms. Instead, there might be a constant hiss of droplets falling through gas, a white noise of precipitation that never varies. As the iron droplets fall deeper into the atmosphere, they encounter increasing temperatures due to the compression of atmospheric layers under their own weight. At some depth, the temperature rises back above iron's vaporization point, and the falling droplets begin to evaporate, returning to the gaseous state they occupied on the dayside. This creates a kind of iron cloud deck, a layer in the atmosphere where liquid iron is present, bounded above by condensation and below by re-evaporation. The iron that re-vaporizes at depth may eventually circulate back up to higher altitudes, perhaps carried by convective motions in the deep atmosphere that bring material up from warmer regions below. If this return circulation is efficient, the iron cycle can sustain itself indefinitely, with the same iron atoms repeatedly vaporizing, condensing, falling, and evaporating again. Each atom might make this journey countless times over the lifetime of the planet. Alternatively, some iron may sink so deep that it becomes sequestered in the planet's interior, removed from the atmospheric circulation that we can observe from Earth. Over billions of years, this process could gradually deplete the upper atmosphere of iron, potentially weakening or even eliminating the iron rain phenomenon. However, the current observations suggest that plenty of iron remains in the observable atmosphere, indicating that the cycle is far from exhausted. The visual appearance of the night side would be dominated by this glowing precipitation against the backdrop of absolute darkness beyond the atmospheric envelope. There would be no stars visible from within the atmosphere. The atmospheric layers above would scatter and absorb incoming starlight, and the planet's own disk would block any light from the parent star. The only illumination would come from the falling iron droplets themselves, and perhaps from the thermal glow of the atmosphere at depth. The transition from terminator to deep nightside would involve a gradual increase in the intensity of the iron rain as more and more of the vapor condenses in the cooling atmospheric stream. The heaviest precipitation might occur some distance beyond the terminator, where temperatures have dropped enough for efficient condensation, but the iron-laden atmospheric stream has not yet been fully depleted. Further into the night side, the rain might become lighter as the remaining iron vapor is progressively removed from the flow. The antistellar point, the location on the night side directly opposite from the star, might represent a region of relative calm in the atmospheric circulation pattern. Here, the day-to-night flows from all directions would converge, potentially creating complex patterns of rising and sinking air. Whether iron rain would be heavier or lighter at this convergent zone depends on details of the circulation that we cannot yet determine from observations alone. The concept of weather on the night side differs fundamentally from our experience of weather on Earth, where changing conditions are the norm and no 2 days are exactly alike. On the night side of WASP-76b, the conditions are essentially static. The same iron rain falling through the same temperatures in the same eternal darkness, without variation. There are no seasons, no storm systems passing through, no clearing skies or approaching fronts to mark the passage of time and change. This permanence extends across timescales that dwarf human history, the iron rain likely falling continuously for billions of years since the planet first settled into its current tidally locked configuration. The rain that falls tonight is essentially identical to the rain that fell 1 million years ago and to the rain that will fall 1 million years from now. The planet exists in a kind of steady state, its atmospheric circulation and chemistry in equilibrium with the constant input of energy from its nearby star. For a listener drifting toward rest, there is something oddly soothing about this image of eternal precipitation, a rain that never stops and never changes. The universe contains such constants, processes that continue regardless of who observes them, phenomena that persist across timescales too long for any individual mind to comprehend. The iron rain on WASP-76b is one such constant, a cosmic drumbeat that marks time on a world utterly unlike our own. In the next part of our journey, we will explore what other exotic chemistries might exist in the atmosphere of this extreme world beyond the iron that has captured so much of our attention. Iron is not the only remarkable chemical story unfolding in the atmosphere of WASP-76b, merely the one that has received the most attention due to its dramatic reign. The extreme temperatures on this world enable chemical processes that would be impossible under the cooler conditions found on Earth, or anywhere else in our solar system. The atmosphere is likely a rich mixture of elements and compounds that we would find utterly alien, a chemistry laboratory operating under extreme conditions. Titanium oxide, a molecule composed of titanium and oxygen atoms, has been detected or suggested in the atmospheres of several ultra-hot Jupiters and may well be present on WASP-76b. On Earth, titanium oxide is used as a white pigment in paints and sunscreens, prized for its ability to absorb ultraviolet light and reflect visible wavelengths. In the atmosphere of an ultra-hot Jupiter, titanium oxide can exist as a gas, floating freely through superheated layers where temperatures climb into thousands of degrees. This molecule plays an important role in shaping the thermal structure of ultra-hot Jupiter atmospheres, absorbing incoming starlight and heating the upper layers. The result is something called a thermal inversion, where temperatures actually increase with altitude rather than decreasing as they do in Earth's lower atmosphere. Such inversions create conditions where the upper atmosphere glows brightly, emitting its own thermal radiation back out into space, like a lantern in the cosmic dark. Vanadium oxide is another molecule that astronomers search for when studying these extreme worlds, a compound that behaves similarly to titanium oxide under high-temperature conditions. Both molecules are strong absorbers of visible and near-infrared light, capable of dramatically altering how energy flows through an atmosphere exposed to intense stellar radiation. Their presence or absence can change the entire character of a planet's climate, determining whether heat stays trapped high in the atmosphere or penetrates deeper. On WASP-76b, the detection of such molecules remains an active area of research, with different observations sometimes yielding different results depending on methods used. The atmosphere is dynamic and complex, likely varying across different regions and altitudes in ways that make simple characterization difficult to achieve with current instruments. What astronomers can say with confidence is that this world contains chemistry unlike anything found on the planets we know best. Sodium and potassium, elements that exist as solid metals under Earth conditions, have been detected in gaseous form in many hot Jupiter atmospheres and are likely present on WASP-76b as well. These alkali metals vaporize at relatively low temperatures compared to iron or titanium, meaning they would be gaseous throughout much of the atmosphere on both the dayside and nightside. Their spectral signatures are relatively easy to detect, making them useful tracers for understanding atmospheric composition and dynamics. The chemistry of ultra-hot Jupiters challenges our intuitions about what atmospheres can contain and how familiar elements can behave under unfamiliar conditions. We are accustomed to thinking of metals as solid materials, substances we can hold in our hands or shape into tools and structures for practical purposes. But on worlds like WASP-76b, these same elements float as vapors, participate in weather cycles, and fall as precipitation in ways that seem almost magical. Magnesium is another element that likely exists in gaseous form somewhere in this planet's atmosphere, along with silicon and other rock-forming elements that constitute solid ground on terrestrial worlds. The temperatures are simply too high for these materials to condense into anything solid, at least on the superheated dayside, where stellar radiation beats down relentlessly. Everything that would be geology on a cooler world becomes meteorology on WASP-76b, rocks transformed into weather. Some models suggest that certain regions of the atmosphere might contain clouds made of corundum, the mineral that forms rubies and sapphires on Earth when combined with trace impurities. Imagine clouds of crystalline aluminum oxide drifting through an alien sky, catching light from a nearby star, and perhaps glittering with colors we can only imagine from our distant vantage. Whether such clouds actually exist remains uncertain, but the temperatures and chemistry would allow for their formation under the right conditions. The nightside of WASP-76b, while cooler than the dayside, still maintains temperatures around 1500 degrees Celsius, hot enough to glow a dull red if you could somehow observe it directly. At these temperatures, many metals that vaporize on the dayside can begin to condense, but others remain gaseous, creating a complex mixture of vapors and droplets swirling through perpetual darkness. The nightside atmosphere is not simply a cooler version of the dayside, but a chemically distinct realm with its own character. Iron rain is the most dramatic example of nightside chemistry, but other metals likely undergo similar transitions as they cross from the superheated dayside into relative darkness. Manganese, chromium, and other transition metals may condense at various altitudes depending on local temperatures and pressures, creating layered precipitation that falls at different rates. The nightside may experience not just iron rain, but a complex mixture of metallic precipitation, a symphony of falling elements. The boundary region between day and night, the terminator, serves as a transition zone, where this complex chemistry unfolds in real time, continuously processing the flow of materials from one hemisphere to the other. Winds carry vapors across this boundary, and as temperatures drop, condensation begins, with different elements precipitating at different points, depending on their individual properties. The terminator is not a static line, but a dynamic weather front, a permanent atmospheric processing zone that never stops operating. Water vapor, so abundant in Earth's atmosphere and so crucial to life as we know it, cannot exist on the dayside of WASP-76b in any stable form. At temperatures exceeding 2000 degrees, water molecules would be torn apart into their constituent hydrogen and oxygen atoms, dissociated by thermal energy too intense for chemical bonds to survive. Any water that once existed on this world, if it ever existed at all, has long since been destroyed by the extreme conditions. This molecular destruction extends to many other familiar compounds that we take for granted on our temperate world spinning around a calmer star. Carbon dioxide, methane, ammonia, molecules that play important roles in the atmospheres of planets throughout our solar system, would all be broken apart on the dayside of WASP-76b. The chemistry here is dominated by atoms rather than molecules, individual elements floating free rather than bonded into the complex compounds we know. Yet on the nightside, where temperatures drop enough for chemical bonds to reform, some of these molecules may reassemble from their constituent atoms floating in the darkness. The perpetual cycling between dayside destruction and nightside reconstruction creates a dynamic chemistry that never reaches equilibrium, always processing and reprocessing the same materials. It is a world in constant chemical flux, never settled, never stable, always transforming. The atmospheric layers of WASP-76b likely show different compositions at different altitudes, with heavier elements sinking deeper, while lighter ones remain suspended higher in the atmosphere. This stratification creates a vertical structure that astronomers can probe using different observational techniques, each sensitive to different layers and compositions. The picture that emerges is not of a uniform atmosphere, but of a complex layered system with its own internal organization. Hydrogen, the lightest and most abundant element in the universe, likely dominates the upper atmosphere, having been retained from the original cloud of gas from which this planet formed. Helium, the second lightest element, probably constitutes a significant fraction as well, creating an overall composition similar to our own Jupiter and Saturn. But mixed into this hydrogen-helium envelope are the exotic vapors we have discussed. iron, titanium, sodium, and others, in concentrations that would be extraordinary by solar system standards. The color of this atmosphere, if human eyes could somehow perceive it directly, would probably be unlike anything in our experience. Perhaps dark and murky from the various absorbing compounds, perhaps glowing with its own thermal emission at certain wavelengths. Different wavelengths of light would reveal different aspects of this alien sky, some absorbed by certain molecules, others scattered or reflected by clouds of condensed minerals. The atmosphere is a filter, selectively processing the starlight that passes through it, in ways that encode information about its composition. Astronomers have detected asymmetries in the atmosphere of WASP-76b that suggest complex three-dimensional structure extending beyond simple day-night differences in temperature and chemistry. The evening terminator, where the dayside transitions into night, shows different chemical signatures than the morning terminator, where night transitions back into day. This asymmetry is direct evidence of atmospheric circulation, wind patterns carrying material in one direction around the planet and creating permanent chemical gradients. The discovery of iron vapor on the evening terminator, but not the morning side, was the key observation that led to the iron rain hypothesis in the first place. Iron vaporizes on the day side, gets carried by winds toward the night side, condenses and falls as rain during the long crossing through darkness, and is therefore absent from the morning side. The pattern makes elegant sense once you understand the wind circulation, a beautiful example of how observation and theory can combine to reveal hidden processes. Similar asymmetries may exist for other elements and compounds, each with its own pattern of vaporization, transport, condensation, and precipitation, depending on individual properties. The atmosphere of WASP-76b is not just exotic in composition, but dynamic in behavior, a weather system operating under rules that we are only beginning to understand. Every new observation adds detail to our picture, revealing complexity that simpler models could not have predicted. The exotic chemistry of WASP-76b represents just one example of what becomes possible when familiar elements are subjected to unfamiliar conditions on distant worlds. Throughout the galaxy, thousands of other ultra-hot Jupiters likely host their own exotic atmospheric processes, each with its own unique combination of elements and conditions. Some may rain different metals, some may have clouds of different minerals, and some may harbor chemistries we have not yet imagined. This diversity is part of what makes exoplanet science so exciting, even as we approach it with the calm wonder appropriate for sleep-friendly exploration of the cosmos. Every world is a natural experiment, a test of how physics and chemistry operate under conditions that could never be replicated in any laboratory on Earth. WASP-76b teaches us about iron rain, but the next world we study might teach us something entirely different. For now, the exotic chemistry of this world remains partially mysterious, with many questions still waiting for answers that will come from future observations. What other metals rain from those alien clouds? What other molecules float through that superheated atmosphere? What surprises remain hidden, waiting for the next generation of telescopes to reveal them? These questions drift with us as we continue our exploration, unanswered but fascinating. The knowledge we possess about WASP-76b comes entirely from light, from photons that traveled 640 light-years across empty space to reach telescopes on Earth. We cannot visit this world, cannot send probes to sample its atmosphere, cannot touch or taste or directly experience any aspect of its extreme environment. Everything we know has been inferred from the careful analysis of starlight, decoded by instruments of extraordinary precision. The espresso spectrograph, whose name stands for Echelle spectrograph for rocky exoplanets and stable spectroscopic observations, is one of the primary tools that revealed the secrets of this iron-reigning world. Mounted on the Very Large Telescope in the Atacama Desert of northern Chile, Espresso can detect incredibly subtle changes in the spectrum of starlight as a planet passes in front of its host star. The precision required is extraordinary, measuring shifts smaller than the width of a human hair from a distance of several meters. When WASP-76b transits its parent star, a tiny fraction of the starlight passes through the planet's atmosphere before continuing its journey toward Earth. This light carries the fingerprints of whatever gases it encountered during that brief passage, with different elements and molecules absorbing specific wavelengths in characteristic patterns. By comparing the spectrum during transit to the spectrum when the planet is not in front of the star, astronomers can determine what the atmosphere contains. The detection of iron vapor required measuring changes in the starlight spectrum that amounted to differences of just a few parts in 10,000, incredibly subtle signals buried in much larger amounts of noise. Extracting such faint signals requires not just sensitive instruments, but sophisticated data analysis techniques developed over decades of astronomical research. Teams of scientists work together, combining observations from multiple transits to build up signal strength and reduce the random fluctuations that might otherwise obscure the truth. The iron signature that Espresso detected was not just a simple absorption feature, but a pattern that shifted across the spectrum during the transit observation period. This shift revealed that the iron vapor was moving, carried by atmospheric winds from the dayside toward the nightside at speeds of several kilometers per second. The Doppler effect, the same phenomenon that makes ambulance sirens change pitch as they pass by, encoded velocity information into the light. By carefully analyzing how the iron signature changed during transit, astronomers could determine not just that iron was present, but where it was located and how it was moving through the atmosphere. The iron appeared strongly on the evening terminator, where winds carried dayside vapor toward the nightside, but was absent from the morning terminator. This asymmetry was the key evidence for iron rain, revealing a precipitation process that removes iron from the atmosphere during the nightside crossing. The Atacama Desert, where the Very Large Telescope stands, is one of the driest places on Earth, a landscape so barren that it has been compared to the surface of Mars. This extreme aridity makes it ideal for astronomical observations, with minimal water vapor in the atmosphere to absorb infrared light or blur the images of distant stars. The thin, dry air above the Atacama allows telescopes to see with extraordinary clarity, capturing light that has traveled for centuries across the cosmos. The Very Large Telescope is actually a collection of 4 main telescopes, each with a primary mirror 8.2 meters in diameter, plus several smaller auxiliary telescopes that can work together. When these instruments combine their observations, they achieve resolving power, equivalent to a single telescope much larger than any of them individually. This technique, called interferometry, allows astronomers to see details that would otherwise be impossible to discern from our distance. Espresso can connect to any one of the 4 main telescopes, or even combine light from all 4 simultaneously, creating an instrument of tremendous power for studying exoplanet atmospheres. The spectrograph itself is housed in a temperature-controlled room deep within the observatory complex, isolated from vibrations and temperature changes that might affect its precision. Every aspect of its design prioritizes stability because the measurements it makes are so sensitive that even tiny disturbances could corrupt the data. The transit method, which Espresso exploits to study atmospheres, was first proposed decades ago as a way to detect and characterize planets around other stars. The basic idea is simple. When a planet passes in front of its star from our perspective, the star's light dims slightly by an amount proportional to the planet's size. For a Jupiter-sized planet like WASP-76b, this dimming is roughly 1%, easily detectable with modern instruments. But the atmospheric information comes from an even subtler effect, the filtering of starlight through the thin ring of atmosphere visible around the planet's silhouette during transit. This ring represents only a tiny fraction of the planet's disk, meaning the atmospheric signal is much smaller than the overall transit depth. Detecting specific elements like iron requires identifying their absorption signatures within this already faint signal, a challenge that pushes instruments to their limits. The first successful detection of an exoplanet atmosphere came in 2001 when astronomers using the Hubble Space Telescope detected sodium vapor around a hot Jupiter called HD 209458b. Since then, the field has advanced tremendously, with dozens of exoplanet atmospheres now characterized to varying degrees of detail. WASP-76b represents one of the most detailed atmospheric studies to date, revealing not just composition, but dynamics. Ground-based telescopes, like the Very Large Telescope, have certain advantages over space telescopes for some types of observations, including larger mirror sizes and easier maintenance. However, they must contend with Earth's atmosphere, which absorbs certain wavelengths, introduces turbulence that blurs images, and adds its own spectral features to observations. Sophisticated techniques have been developed to correct for these effects, including adaptive optics systems that deform telescope mirrors in real time to counteract atmospheric distortion. For spectroscopic observations, like those that revealed iron rain on WASP-76b, the main challenge is separating planetary signals from telluric contamination, spectral features introduced by Earth's own atmosphere. This requires careful modeling of how our atmosphere affects light at different wavelengths and times, subtracting these effects to reveal the true planetary signal underneath. The process is painstaking, requiring expertise built up over years of experience. Space telescopes avoid atmospheric contamination entirely, but face their own challenges, including limited mirror sizes, constrained by rocket payload fairings, and the difficulty of repairs once in orbit. The James Webb Space Telescope, with its 6.5-meter segmented mirror, has observed many exoplanet atmospheres with unprecedented sensitivity since its launch. Future space telescopes with even larger mirrors may reveal details about worlds like WASP-76b that remain beyond our current reach. The observations that revealed iron rain required patience measured in hours, tracking the planet across multiple transits to build up sufficient signal for confident detection. Each transit of WASP-76b lasts approximately 3.7 hours, during which the planet crosses the face of its star as seen from Earth. Astronomers typically observe for longer than this, capturing baseline data before and after transit to establish comparison spectra. Not every transit observation yields useful data, as weather conditions, instrument issues, or other problems can compromise or prevent observations entirely. Scheduling telescope time is competitive, with many astronomers seeking access to instruments like Espresso for their own research projects. The team that discovered iron rain on WASP-76b earned their telescope time through a rigorous proposal process, convincing review committees that their science case justified the resources. Once observations are complete, the real work of data analysis begins, a process that can take months of careful examination before results are ready for publication. Every potential source of error must be considered and addressed. Alternative explanations must be ruled out, and conclusions must be tested against the data from multiple angles. The iron rain detection passed all these tests, earning acceptance from the scientific community as a robust and reliable result. The instruments we build to study distant worlds represent the accumulated ingenuity of countless engineers, scientists, and technicians working together over decades. Espresso alone required more than 10 years of development before achieving first light in 2017, with hundreds of people contributing to its design and construction. The mirrors, gratings, detectors, and control systems all represent the state-of-the-art in their respective fields. Behind these instruments lie centuries of scientific progress, from the first telescopes built in the early 1600s to the sophisticated adaptive optic systems of today. Each generation of astronomers has built upon the work of those who came before, refining techniques, developing new technologies, and pushing the boundaries of what can be observed. The detection of iron rain on a world 640 light-years away is the culmination of this long history. Future instruments will push these boundaries even further, revealing details about exoplanet atmospheres that remain hidden to current technology. The extremely large telescope, currently under construction in Chile, will feature a primary mirror nearly 40 meters in diameter, gathering more than 10 times the light of any existing telescope. When it begins operations in the late 2020s, it will transform our ability to characterize worlds like WASP-76b. The patience required for astronomical observation mirrors the patience required for scientific understanding itself, a willingness to work slowly toward answers that may take years or decades to fully emerge. We cannot rush the universe to reveal its secrets on our schedule. We can only build better instruments and wait for the right conditions to make observations. The iron rain of WASP-76b was unknown until the technology and opportunity aligned to reveal it. There is something meditative about this approach to knowledge, this acceptance that understanding comes gradually rather than all at once in sudden revelation. Astronomers plan observations years in advance, submit proposals, wait for telescope time, collect data, analyze results, and publish findings. A cycle that repeats throughout careers spanning decades. The steady accumulation of knowledge, paper by paper, and observation by observation, eventually transforms our understanding of the cosmos. Tonight, telescopes around the world continue their patient work, gathering light from countless stars and the planets that orbit them, adding incrementally to human knowledge. Somewhere, right now, an astronomer is analyzing data from an observation made months ago, looking for patterns that might reveal something new about a distant world. The work continues whether we are awake or asleep, a permanent vigil that never ends. WASP-76b is extraordinary, but it is not unique. The galaxy contains many worlds that challenge our expectations about what planets can be and how they can behave. In the decades since the first exoplanet discoveries, astronomers have catalogued thousands of worlds. revealing a diversity that far exceeds anything anticipated from studying our own solar system alone. Some of these worlds make WASP-76b seem almost ordinary by comparison. The category of ultra-hot Jupiters, to which WASP-76b belongs, contains dozens of known members, each with its own extreme characteristics shaped by proximity to its parent star. Kelt 9b, orbiting a star in the constellation Cygnus, reaches dayside temperatures exceeding 4,000 degrees Celsius, hotter than many small stars and hot enough to dissociate hydrogen molecules into individual atoms. This world exists at the boundary between planet and something else entirely. WASP-121b, another ultra-hot Jupiter, shows evidence of metals including iron and magnesium escaping from its atmosphere entirely, stripped away by intense radiation and carried off into space. This planet is slowly evaporating, losing mass to the void in a process that will continue for billions of years until perhaps nothing remains but a bare rocky core. The extreme environment is literally destroying the world, atom by atom. Hot Jupiters were among the first exoplanets ever discovered, surprising astronomers in the 1990s who expected to find planetary systems resembling our own with gas giants in distant orbits. The discovery of 51 Pegasi b in 1995 revealed a Jupiter-sized planet orbiting its star in just 4.2 days, far closer than Mercury orbits our Sun. This single discovery transformed our understanding of how planetary systems form and evolve. Since then, hundreds of hot Jupiters have been catalogued, revealing a population of worlds that migrated inward from their formation locations in the outer reaches of their planetary systems. The migration process likely occurred early in these systems' histories, driven by gravitational interactions with the disk of gas and dust from which planets form. Some hot Jupiters may have displaced or destroyed other planets during their inward journey. Ultra-hot Jupiters represent the most extreme members of this population, worlds that orbit so close to their stars that their atmospheres behave more like stellar atmospheres than planetary ones. The temperatures are high enough to ionize atoms, creating plasma conditions that blur the distinction between planet and star. WASP-76b exists in this extreme regime, its chemistry driven by conditions that would vaporize any spacecraft we could possibly build. Beyond hot Jupiters, astronomers have discovered planets that rain glass, worlds where silicon particles condense in the upper atmosphere and fall through superheated lower layers. HD 189-733b, a planet about 1,000 light-years from Earth, likely experiences this exotic precipitation, with silicate droplets forming in nightside clouds. The glass rain falls sideways, driven by powerful winds that circulate around the planet, reaching speeds of several thousand kilometers per hour. Some worlds orbit so close to their stars that they are tidally disrupted, stretched into elongated shapes by gravitational forces that would tear Earth apart entirely. Others orbit in such eccentric paths that they experience extreme temperature swings, roasting during close approach and freezing during the distant portion of their orbits. The variety of planetary configurations that nature has produced far exceeds what theorists imagined before the era of exoplanet discovery. Lava worlds, planets with surfaces covered in molten rock, represent another category of extreme environment found throughout the galaxy. 55 Cancriae, a super-Earth about 40 light-years away, may have a surface of flowing magma on its permanent dayside, with temperatures approaching 2,000 degrees Celsius. This world was once thought to be a diamond planet, with a carbon-rich interior, though current evidence suggests a more complex and uncertain composition. The discovery of each new extreme world teaches us something about the range of conditions that can exist on planets throughout the universe. WASP-76b teaches us that iron can participate in weather cycles, that metals can rain from skies, that the familiar elements of our periodic table can behave in unfamiliar ways. Each lesson expands our understanding of planetary science beyond the limited examples available in our own solar system. This expansion of knowledge has practical implications for understanding how planets form, evolve, and potentially host life under various conditions throughout the galaxy. While ultra-hot Jupiters are certainly not habitable, studying them helps us understand atmospheric physics and chemistry in ways that apply to all planets. The techniques developed to detect iron rain on WASP-76b can be adapted to search for biosignatures on more temperate worlds. The diversity of extreme worlds also provides context for appreciating how unusual or typical our own Earth might be within the broader population of planets. We know of no world exactly like Earth. A rocky planet with liquid water oceans, a protective atmosphere, and stable conditions for billions of years, though the search continues. Understanding the extremes helps us understand the middle, the range of conditions where life as we know it might possibly emerge. Some ultra-hot Jupiters are slowly being destroyed by their parent stars, their atmospheres stripped away by intense radiation over millions of years. WASP-12b, orbiting an F-type star similar to the parent of WASP-76b, is losing mass so rapidly that it may be completely consumed within the next 10 million years. The planet spirals ever closer to its star, tidally distorted into an egg shape, its material feeding onto the stellar surface. This destruction is not violent or sudden, but gradual and almost gentle, a slow surrender of planetary material to stellar gravity over timescales that dwarf human civilization. The planet dims slightly over decades as more atmosphere escapes, a decline that astronomers can actually measure with sufficiently precise observations. WASP-12b is dying, but its death will take longer than humans have existed as a species. Other ultra-hot Jupiters appear more stable, having reached equilibrium configurations that may persist for billions of years as long as their parent stars continue shining steadily. WASP-76b seems to fall into this category, massive enough to retain its atmosphere against the stellar onslaught, distant enough to avoid tidal disruption or orbital decay. The iron rain has likely been falling for a very long time and will continue for ages to come. The technology that allows us to study these extreme worlds continues to advance, promising even more detailed observations in the years and decades ahead. The James Webb Space Telescope has already observed multiple ultra-hot Jupiters, detecting molecules and mapping temperature variations across their surfaces with unprecedented precision. Future telescopes will push further still, perhaps eventually imaging these worlds directly rather than inferring their properties from starlight alone. The Atmospheric Remote Sensing Infrared Exoplanet Large Survey, or AREL, is a European Space Agency mission planned for launch in 2029 that will systematically study the atmospheres of roughly 1,000 exoplanets. WASP-76b will likely be among its targets, contributing additional data to our understanding of this iron-raining world. Each new observation adds detail, refines models, and occasionally reveals surprises. Ground-based, extremely large telescopes will complement these space-based observations, providing high-resolution spectroscopy that can detect individual elements and track their motion through alien atmospheres. The combination of space and ground observations, each with its own strengths and limitations, creates a more complete picture than either could provide alone. WASP-76b will remain a target of interest for many years as our instrumental capabilities continue to improve. The extreme worlds we have discovered represent a tiny fraction of those that must exist throughout the galaxy, limited by our current ability to detect and characterize planets around distant stars. Most exoplanets remain unknown, their existence unconfirmed, their properties unmeasured by any instrument on Earth or in space. The catalogue will grow as technology improves, revealing new extremes we have not yet imagined. Some of these undiscovered worlds likely host phenomena even stranger than iron rain, chemical and physical processes that will challenge our understanding when eventually revealed. The universe has proven consistently more creative than human imagination, presenting worlds that theorists did not predict and conditions that textbooks did not describe. Every new discovery carries the possibility of surprise. WASP-76b was itself a surprise when its iron rain was first detected, a phenomenon that made intuitive sense in hindsight but had not been specifically predicted beforehand. The observers who detected the iron signature were looking for atmospheric information, but did not know what exactly they would find. Their openness to unexpected results allowed them to recognize something new when the data revealed it. The study of extreme worlds connects to broader questions about the nature of planets and what defines them as a category of cosmic objects. At what point does an ultra-hot Jupiter become so hot that it functions more like a star than a planet? Where is the boundary between atmosphere and space when material continuously escapes into the void? These questions have no simple answers. Definitions matter less than understanding, and what we understand is that the universe produces a continuous spectrum of objects, from small rocky worlds to giant stars. Planets like WASP-76b occupy an interesting region of this spectrum, displaying behaviors that mix planetary and stellar characteristics in ways that illuminate both categories. They are laboratories for extreme physics, natural experiments that test our theories. The iron rain falling through the nightside atmosphere of WASP-76b represents just one phenomenon among countless others occurring on extreme worlds throughout the galaxy at this very moment. Somewhere, glass is falling sideways through supersonic winds, magma is flowing across permanent daysides, and atmospheres are escaping into space from planets too close to their stars. The universe is busy with strange weather. As we contemplate these extreme worlds, a sense of perspective settles over our understanding of our own planet and its place in the cosmic order. Earth is extreme in its own way, extreme in its moderation, its stability, its capacity to support liquid water and complex chemistry for billions of years. This apparent ordinariness is itself extraordinary when viewed against the backdrop of iron rain and glass storms. The conditions that make Earth habitable required a specific combination of circumstances: distance from the Sun, planetary mass, atmospheric composition, magnetic field strength, and countless other factors that aligned to create our temperate home. Change any of these significantly, and we might have ended up with a world as hostile as WASP-76b, where no life could possibly emerge or survive. This is perhaps the deepest lesson that extreme worlds teach us: appreciation for the delicate balance that sustains our existence on this small blue marble, circling an ordinary yellow star. The universe could easily have been otherwise, and in most places, it is otherwise. Too hot, too cold, too violent, too barren for life as we know it. We are fortunate inhabitants of an exceptional world. The iron rain continues falling on WASP-76b as you listen to these words, a precipitation of liquid metal descending through darkness on a world 640 light-years distant. The winds that carry iron vapor from the dayside continue blowing, driven by temperature differences that have existed for billions of years and will persist for billions more. Nothing about this alien weather depends on human observation. This is one of the quietly profound aspects of astronomical discovery. The realization that the phenomena we detect have been occurring for ages before we learn to look for them and will continue long after we stop watching. The universe operates on its own terms, indifferent to our awareness, proceeding through its physical processes, whether anyone notices or not. Our observations change us, not the things we observe. WASP-76b existed as an iron-raining world for perhaps 4 billion years before humans evolved on Earth, before life on our planet climbed from the oceans onto land. The superheated dayside vaporized iron while early fish were developing the first bones, while dinosaurs rose and fell, while ice ages came and went on our distant world. The rain fell through all of human history, unremarked and unknown. The light from WASP-76b that reaches Earth tonight began its journey around the time that Isaac Newton was alive, when telescopes were simple tubes with small glass lenses, and the very concept of planets around other stars was pure speculation. Those photons traveled through space while humanity invented electricity, split the atom, landed on the moon, and built the very instruments that now catch them after their long journey. The light carries no knowledge of what it will find at its destination. By the time new light from that distant world arrives in future centuries, humanity will have changed in ways we cannot predict from our present vantage point. The civilizations of 500 years from now, if they still study the sky, will have technologies and understandings that would seem magical to us today. Yet the iron rain will still be falling, unchanged by whatever transformations occur on Earth, patient and perpetual. There is something restful about this cosmic continuity, this assurance that the universe proceeds steadily, regardless of human concerns or anxieties that trouble our sleep. The storms on WASP-76b are not affected by politics or economics, by personal worries or global crises that seem so pressing in our daily lives. They simply continue, as they have for eons, as they will for eons more. The imagination reaches toward that distant world, trying to picture what cannot truly be pictured. Skies glowing with thermal emission, clouds of vaporized metal, rain falling through temperatures that would melt steel. Our minds are not equipped to fully comprehend such extreme conditions, having evolved to understand the gentle environment of Earth. But we can gesture toward understanding, build approximate images that capture something of the truth. Imagine floating somehow in the upper atmosphere of that nightside, surrounded by darkness, broken only by the dull red glow of superheated gases below, and the cold stars wheeling overhead. Iron droplets fall around you, each one glowing faintly with residual heat, streaking downward through the thick hydrogen atmosphere, toward depths no light could ever reach. The wind carries you eastward, toward the terminator, toward the distant glow of the eternal dayside just beyond the horizon. This imaginary journey is impossible. No spacecraft could survive. No human could exist there for even a fraction of a second. But the imagination knows no such limitations. We can visit in thought places our bodies could never go, explore environments that would destroy any physical probe we could build. The iron rain falls through our minds, as readily as through alien skies. The constellation Pisces, where WASP-76 and its planet reside, is visible from most of Earth during autumn and winter months in the northern hemisphere. If you know where to look, you can point toward the region of sky where this iron-reigning world continues its eternal orbit, too faint to see but present nonetheless. The light reaching your eyes from nearby visible stars traveled a similar path through space. Ancient civilizations named this constellation after fish, seeing patterns in the scattered points of light that suggested shapes from their everyday experience and mythology. They could never have imagined that within those familiar star patterns lay worlds of liquid metal rain and temperatures that vaporize rock. The universe they knew was small, contained within the sphere of fixed stars that circled the Earth. Our universe is larger, stranger, and more wonderful than any ancient astronomer could have conceived in their most imaginative moments. We know of worlds that rain iron, worlds that rain glass, worlds covered in eternal oceans, worlds with surfaces of permanent magma. The catalogue of cosmic wonders grows with each passing year, each new telescope, each observation that reveals something previously unknown. The study of distant worlds like WASP-76b is ultimately a human activity, pursued by people who chose to spend their careers looking upward rather than down at the ground beneath their feet. These astronomers and engineers, data analysts and telescope operators form a community dedicated to expanding the boundaries of human knowledge outward into the cosmos. Their work continues day and night across continents and generations. Somewhere right now, a graduate student is writing code to model the atmospheric dynamics of an ultra-hot Jupiter, testing theories against observations to see which ideas survive contact with reality. Somewhere else, an observer is preparing for a night of telescope time, checking weather forecasts and instrument calibrations in preparation for gathering photons that traveled for centuries. The enterprise of discovery never sleeps entirely. This ongoing effort represents something admirable about humanity: the willingness to invest time and resources in understanding things that have no practical application, that offer no material benefit, that simply satisfy the deep curiosity that seems embedded in our species. We want to know what is out there, even when what is out there can never affect our daily lives. The iron rain of WASP-76b matters because we have decided it matters. The night deepens wherever you are, and the thoughts of distant worlds settle into something softer, less focused, more dreamlike in quality and texture. The extreme temperatures and exotic chemistries become abstractions, beautiful patterns that the mind holds lightly rather than grasps tightly. Understanding relaxes into appreciation, and appreciation fades towards simple awareness. WASP-76b continues its orbit as your thoughts grow quiet, completing another circuit around its star every 1.8 Earth days without pause or hesitation. The iron rain falls through perpetual night, has fallen for billions of years, will fall for billions more. A rhythm as steady as any heartbeat, as reliable as any tide. The universe keeps its own time. The light from that distant world streams through space at 300,000 kilometers per second, carrying information about temperatures and chemistry and winds that we have learned to decode with instruments of extraordinary precision. Some of that light will arrive at Earth tomorrow, bringing news of conditions that exist right now on that superheated world. The conversation between humanity and the cosmos continues. Other extreme worlds orbit other stars throughout the galaxy, each with its own strange weather, its own exotic chemistry, its own story that we may or may not eventually learn to read from the faint signals encoded in starlight. The universe is vast beyond comprehension, filled with more worlds than any catalogue could contain, more phenomena than any lifetime could explore. WASP-76b is one data point in an infinite dataset. Yet this one world, with its iron rain and superheated atmosphere, has touched your awareness tonight, has expanded slightly the territory of your imagination, has reminded you that the cosmos is stranger and more wonderful than ordinary experience suggests. Tomorrow you may forget the details, the temperature numbers, the orbital period, the distance in light years, but something may remain. What remains is the sense of scale, the quiet wonder, the appreciation for a universe that produces such extraordinary phenomena on worlds we will never visit but can always imagine. The iron rain falls whether we remember it or not, but we are richer for having contemplated it, even briefly, even drowsily, even as sleep begins to claim attention. The stars outside your window, if you can see them, are the same stars that astronomers study with billion-dollar telescopes on remote mountain tops. The same stars whose light carries encoded messages about the worlds that orbit them. You share this sky with every human who has ever looked upward and wondered, from ancient observers who named the constellations to modern scientists who decode the chemistry of alien atmospheres. The extreme weather of WASP-76b is happening right now, at this very moment. Whether or not anyone observes it, whether or not anyone remembers that such a world exists. The iron vaporizes on the eternal dayside. The winds carry it toward darkness. The rain falls through the nightside atmosphere, and the cycle continues as it has for eons. The universe operates on its own schedule. Your own breathing has perhaps slowed as these words have accumulated. Your own thoughts growing softer and less distinct as the journey through alien skies approaches its end. This is as it should be. The wonder was never meant to excite but to settle, to expand the mind and then let it rest, to remind you of cosmic beauty before releasing you to sleep. The iron rain will still be falling when you wake, will still be falling next week, next year, next century, for as long as that world orbits its star and temperatures maintain the conditions for this exotic precipitation. Nothing you do or fail to do will change this distant weather, this alien phenomenon that proceeds on its own terms in a corner of the galaxy you can point toward but never reach. There is peace in this independence, in knowing that the universe continues its operations regardless of human attention or intention. The extreme worlds and their strange weathers, the distant stars and their orbiting planets, the vast distances and ancient light, all of this exists outside the circle of human concern, beautiful and indifferent. The iron rain is real. The 640 light years of empty space separating that world from Earth are real. And you are real, breathing gently, resting quietly, perhaps already beginning to drift towards sleep as these final words carry you toward dreams. The cosmos continues while you rest, iron falling through alien darkness, stars shining across the void, light traveling toward destinations it will reach in centuries to come. The journey we shared tonight reaches its end, but the universe goes on, patient and vast and full of wonders yet to be discovered. Good night from the Drowsy Astronaut. Sleep well, and we'll explore the cosmos together again soon.